Hi everyone. So let's look at the second problem of physics application of first order equations. And this is a gravity problem. So I told you there are two types of problems, and this is about gravity. And obviously with the second law of Newton's second law of motion. And so it says that F is equal to ma. And here a is acceleration, which for our purposes is derivative of the velocity. Okay, because we're going to always solve this in terms of velocity, so that it becomes the first order, because otherwise if we think of a as double y, the double derivative of y, then it will be second order, which is something we're going to deal with later. Okay, and m of course is the mass here. And so what is the force here? So let's read the question. So space explorers have landed on a small moon, and they calculate that its gravitational constant is 0.5 meter per second squared. So let's write that up. That's the g, of course, right? A half. It's easy to work with a fraction and with the decimal. Experiments showed that the atmosphere of the moon causes a resistance which is proportional to the square of the velocity of an object. So we have, so the force F here consists of two things. We have the gravitational force, minus mg, write it in there. And then we have a resistance force, and they tell us that the resistance force is proportional to the square of the velocity. Now, there is what I have to put here. I have a plus or minus, and that's why we always better to make a picture here. So remember, our y-axis is always pointing upwards. That's a standard assumption that we make. That's why we have a negative sign here, because gravitation makes you go down against the direction of the y-axis. And so what we are dealing with is we have a probe over a rocket that is going upwards. So always determine the direction in which you're going. Is it positive or negative? So the velocities here have to be positive velocities if you go upwards, right? And the velocities will be negative if you go downwards. Okay. So what is that? So it is a negative here. Why? Because your atmosphere is slowing you down. So it's against your movement. So it acts negatively, right? Against what you're trying to do. Okay, that's why it's a negative sign. Okay, so we can write down everything that we have. Okay, let's read further what it is. It says proportional to the square velocity of an object, and is equal, so I'm here, is equal to 100 Newton when the velocity is 2m squared. This is what we're gonna use to calculate k. They decide to launch a 25 kilogram probe, right? Sorry, I didn't read it, I said it already. It's a probe that's gonna be launching from the surface, so it's upwards, with an initial boost of 5 meters per second. After how many seconds will the probe reach its highest point? Okay, so we have all these constants here that we have to determine. We have already talked about g. Let's talk about k now. So we say, it says here that this information, so let's color it, that you see where it comes. So 100 Newton, that is the resistance force, and this is when V is equal to 2. So we plug in that 2 square here, so there's 4k. So we see that k, let me write it black now, we see that k is 25. Okay, so this is 25 V square. Okay, what else do we need? G we have, m, we have to determine m. How do we determine m? M is the mass. Now be careful, don't say, oh, 25 kilogram probe. No, it is, at the time of launch, it weighed 25 kilogram. That means its weight at the surface of that moon is 25 kilogram. That is how it pushes, if you put it on a scale, that is the force it pushes onto the scale. But that is not its mass. What does that mean? So this information, as we boxed it here, this means that the Gm, this is the force, with a positive sign here because this is positive, we always take weights positively, right? So Gm is equal to 25. Okay, that is if we are on Earth, then we have to do G, the value for G at Earth, and that tells us what the mass is. Okay, so the mass here is, but we know also what G is. G is a half, right? So let me work it right. So a half, M is 25, so M itself is actually 50. So the mass is 50. It's also measured in kilogram, which is a little bit, I never really understand these units too much, but let's not talk about that now. Okay, we needed all that because now we can write down the equation, right? So we have MA, which is MV prime, so let me write down first in general. So we have, this was our equation, right? Right, I put this together with this and that here. And so now we know what all these constants are. 50 v prime is equal to minus 50 times a half. Well, that is the weight, we know that. Minus k, which was 25 v square. So we get minus 25 minus 25 v square, or we can factor out the minus 25 and get 1 plus v square, and then we can cancel, divide both sides with 25, so we get 2 v prime equals minus 1 plus v square. Great. We know this is separation of, well, this is a, okay, what is this? It is technically, it's not linear. It's not a linear first order differential equation because v comes with the power 2. However, it is a separated variables. Right? The variables are, remember, what are the variables here? So this is separable equation because the variables are v and t, right? And we can put all the v's on one side, but there are no t, so there's nothing going to be there on the other side. So we get minus 2 v 1 plus v square equals, what do we get here? 2v prime, whatever, v minus 2v prime over 1 plus v square, and here we get, well, let's keep the minus sign at that side, I guess. Oh, sorry, that's, oh, okay, let me fix this, because it is, okay. So this, and have a minus 1 here, and it perhaps more telling if I write it this way, then I know what the variables are and what kind of thing that, how my integrals are going to go. So we have separated the variables, so we can integrate. What is the integral of this one? Okay, 1 plus v square, that is a special function. That's the derivative of a special function. Remember, the derivative of arctangent is 1 over 1 plus t squared. So these are the kind of things we need to know in order to solve this, right? So we know that this is 2 times arctangent of v, that's the antiderivative of the left-hand side, and on the right-hand side, that is just minus t plus a constant. Let's call it d for now. Or let's call it c, because I don't think I'm going to change it. Okay, there's c. Okay, so, oh yeah, well, no, I see. I'm going to divide both sides by t, so I get arctangent of v is minus, well, let's write it this way. I'm going to keep it c, sorry. C minus t divided by 2. Let's just keep it that way. And therefore, we know that v, we can make it explicit. And to do it explicit, we have to take the arctangent is the inverse tangent, so it cancels with tangent. So v is equal to the tangent of c minus t over 2. Okay. Right. So what is c? Can we determine c? That's the question. No? So what is c? Well, we haven't used the initial condition yet. What was the initial condition? Is that at time, sorry, give me 1 sec here, guys. I want to double check here. Where's my formula here? Sorry. Here. So what we know at time t equals 0, the moment of launch of that probe, it had an initial velocity, and this is the only thing that we have not used yet, right? So yeah, okay. I saw that I boxed the 100 in orange, but I should have also boxed this one because that is what we used here in this calculation here. I just want to make sure that you see all the numbers are being used now. So 5 meters per second, that is the initial boot, that's the initial velocity. So we get that t0 v is 5. Did I say 5? Yeah, 5. Okay. So if I plug this in, I see 5 is equal to the tangent of c over 2. So we see that the arctangent of 5 is c over 2, or in other words, 2c is twice the arctangent of 5. Now we can figure out what that is. Let's do. So 5 inverse tangent times 2, that's about 2.7. That's my C. And this is measured in seconds, right? So we are working now in seconds. Always pay attention a little bit to the units. As I said, I'm not so concerned with units, and I'm not going to be strict with that. But yeah, the only thing you have to be a bit careful about is for instance, if something is in seconds and another part is set, say, in hours, so you have to convert. But normally, I try to give problems that you don't have to do these conversions, unless it's very similar. Sometimes it's in order to write, let's say, 10,000 meters, it's easier to write 10 kilometers. Okay, so this kind of thing, especially in the decimal system, in the metric system, it's very common to do this kind of little changes. Okay, so instead of writing 25,000 grams, I write 25 kilograms. But as long as then everything is in the same, either kilograms or grams or whatever your unit of measure is, make sure that it always matches. Okay, here we are. So yes. Now the question was, at what time will it reach its highest destination? Okay, so highest point. Now let's see what happens. Well, let's see what happens after it reaches the highest point. It's falling down, right? Then its velocity will become negative. So what it says is this velocity should be positive until it's at its highest points, and then the velocity becomes negative. In other words, highest point is reached when the velocity is 0. Okay, but when is the velocity 0? So we have now our, sorry, I should plug this in here, right? So we know that, let me write it here. I haven't put in my constant. So V is equal to the tangent of C, which is 2.7, minus T over 2. Okay. Right. So V is 0. When is V 0? Well, we put this equal to 0 and solve for T. So 0 is the tangent of 27 minus 2.7, 2.7 here, over T. When is this 0? When is the tangent 0? The tangent, which is sine over cosine, is 0, and the sine is 0, which is if the angle is 0. So this is equivalent with 2.7 minus T equal to 0. 2.7 divided by 2 equals 0, but that's of course the same as, in other words, if T is 2.7. So after 2.7 seconds, the probe is at its highest that it ever will be. And okay, that's not long, right? Because of course gravitation is pulling you down. But okay, it's like 1 Mississippi, 2 Mississippi, 3 Mississippi, and after 3 Mississippi it's already coming down again. Now, we cannot calculate, at this moment we haven't calculated how high it will go up. We're not going to do that, but we know at least when this is going to happen. Okay? All right. I want to, this is the end of it, but I want to point out some a small feature here that is kind of interesting to notice, is that if I would change the initial speed, you say, okay, 2.7 is not long enough. I'm gonna make it go hop higher. So instead of 5 meters per second, so let's put, I'm gonna do this in red. Let's say instead of 5, I'm gonna say let's do 15 meters per second, 10 times as fast. Okay. So what changes then? Well, the only thing that changes is here, right? So this would be 50. Okay. So we have to do the arctangent of 50. So we get 2 times arctangent of 50. So okay, let me calculate that for you. So 50, the arctangent, times 2, that is 3.1. Not much of a gain. 0.4 seconds, it lasts longer. But I have to put 10 times more energy in it to make it go up. So this kind of tells, this is a kind of a problem which you have with launching a rocket, is that the initial velocity that you give it to it is really not helpful. The initial boost, you're going to have to keep boosting it up, and that's why you have, it's not that it's not that we should. When initial boost, we think you could think of it as catapulting. Yeah, we would catapult it into the air, but then there is nothing doing anymore. There's no engine anymore, right? We just catapult it into the air. But if you do that, it doesn't matter whether you do it with 5 meters per second or 50 meters per second. It's not going to be much different. And if you don't believe me, let's put in a ridiculous 10,000 or something like that. So what it would be if instead of 50, I put 10,000, which is an enormous boost that I would give. So what would that do? .1, the same. Why is that? Well, that's because an arctangent is never bigger than pi over 2. So no matter how fast you throw it up, it's always bounded by pi over 2. And so this quantity is always so this quantity will be always less than 2 times pi over 2. In other words, it's going to be less than pi. Or equal to, but equal to it only when you have enormous huge numbers. So you're never going to do much better than 3.1, therefore, 3.14, 3.1. Okay? So that is a strange thing, right? So catapulting with a lot of power of not power, it's, as far as vertical height is concerned, it doesn't help you. Of course, it will help you if you put the catapult in a slanted direction. If you shoot it that way, it's the higher the speed you give it here, the further it will go in the horizontal direction. But in the vertical direction, it will always be the same. And the height it will ever reach is about and it will always be about 3. No, I'm not saying the time it takes to reach its highest point. I should be careful. I'm not saying that the height will change because it depends on the velocity, but the time, sorry, I should have made it more clear. The time that it takes is kind of almost independent of your initial boost that you give it. But therefore, if you want to launch a rocket, you cannot just catapult it. You have to put an engine on there that keeps fighting against gravity and atmospheric resistance. All right, that's all for the preparation. So be very careful with the units, with the numbers. As I said, numbers should be relatively nice. Of course, at some point there will be decimal numbers, especially if we have these functions, tangents and arctangents are coming in. But nothing ugly. Right, everything is neatly small. It's contained. If you get weird numbers, try over again. Especially if the weird numbers come all the way in the beginning. At the very end, as I said, because we're putting in special values and so initial conditions, then you could have a bit more, but random numbers. But in the beginning, you should have nice, clean formal functions. If not, then something probably is wrong, and try over again. And also pay attention always to, as I said, to the units. I'm not insisting on the units, but make sure that the units match. That don't get fooled by a little thing like that. Okay, so I hope you do okay on the quizzes.